Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. This is going to be a good one. It's going to be a pretty quick one. This section is going to introduce some new topics that are very important, but they're also relatively simple. They're not gonna involve a bunch of steps like line integrals or flux integrals do. But they are going to help us do flux integrals when we get to 17.7 and 17.8. So they'll be very important. Um, The main idea of this section, 17.5, is divergence and curl, which are two sort of like derivative operators that we can use on vector fields to get information about those vector fields. So I kind of want to explain what they mean a little bit before I talk about how we're going to get them. Um, the classic interpretation for the divergence of a vector field is that the divergence sort of measures like point by point across the entire vector field. The divergence will give you a sense of which points are sources, which is to say, like from that point in the vector field, things are sort of pushing outward, and which points on this vector field are sinks, which is to say, at that point on the vector field, things are pulling inward. So in these vector fields, we have arrows, vectors, things going around everywhere. These are forces, these are flows, things are moving. So at some points you'll get these areas where things are sort of pushing outward. Some places you'll get points where things are pushing inward. Those are sources and sinks, and the divergence will give us a sense of which one is which. The curl will tell us about the rotational properties of the vector field. So it's another derivative operator that we're going to do to vector fields, and the output of that sort of operator will sort of say if you imagine placing like a small ball in a spot on a vector field, like if that ball is fixed in place, so it's not going to move and flow with the vector field, but it can spin, will the forces and the flow of this vector field cause it to spin? And how fast will it cause it to spin? That's what the curl tells us, how much things are spinning around, or spinning to the left, spinning to the right at any given point on the vector field. So that's what they mean, uh, sort of generally. I I got really curious one day, and I asked some of the folks in the electrical engineering department what they mean like practically in electrical engineering, and it's been a while since I had this conversation, but I think if you have a vector field that represents an electric current, like along a path, the curl of that vector field represents the magnetic field associated with that electric current. I might be wrong about that. I'm not an electrician or an electrical engineer. I'm just kind of faking it. I just do the math. But please ask your expert electricians and electrical inclined people what curl means, and hopefully they will give you a much more thorough and compelling explanation than I can. I do know for sure that curl and probably also divergence as well are very important in the field of electrical engineering, so that's why we're talking about them. You'll need this information eventually. So that's what curl and divergence mean. That is sort of physically what they represent, or how you would interpret these things. Most of what we're going to do with them is just going to be finding them mathematically. We're going to talk about how to get them, if you have a vector field, how do you get the divergence of that vector field? If you have a vector field, how do you get the curl of that vector field? And to do those things, we need to talk about the del operator. The del operator looks like this. It's like an upside down delta or upside down triangle. And you have seen this operator before. You've seen this operator with respect to gradients. This is the thing that gives us gradients. So up till now, we've used this thing on real number valued functions to turn those real number valued functions into vector fields, right? Like if we have a function where like f of x comma y, if this is a function that returns values as numbers, it might look like something like x squared y minus the sine of y, right? This function returns numbers. If you interpret those numbers as altitudes above the xy plane, or below, I guess, if they're negative, then this is the kind of function that gives you a surface. And if you take the gradient by using this sort of del operator, you're going to take the derivative with respect to x, and you'll get 2xy, and you'll attach an I to that piece, right? This is derivative with respect to xi, and you'll take the derivative with respect to y, and you'll get x squared minus cosine of y, and you'll attach a j to that piece. This is the derivative with respect to y, j. And this is what del does as an operator. It's derivatives, it's partial derivatives attached to unit vectors. And if you do it to this real valued function, you get a vector. You get a vector valued function. This is a vector field now. So the real question of this section is, what happens if you try to apply this del operator to something that is already a vector? So this is us applying it to a scalar, and we get a vector. But if del sort of fundamentally is some sort of vector thing, and we apply it to other things that are also already vector things, what does that look like? And how do we apply that? And the answer is we apply it in two different ways. You can do a dot product, and that gives you divergence. Or you can do a cross product, and that gives you curl. So we'll do a couple examples of those things, what those things look like. But first, I guess I just talked about the del operator. I want to formally define this. The del operator means partial derivative with respect to x, I, plus partial derivative with respect to y, j, and then if we're working in 3 dimensions, which we sometimes will be, there'll be a partial derivative with respect to z, k. So this is what the del operator means. It is a vector. It is a vector that's sort of made out of partial derivatives, and that's why it's not like itself an actual vector with like a magnitude. It's a vector that's like made out of operators. The I component of this vector is the operation to take a derivative with respect to x. And the j component of this vector is the operation to take a derivative with respect to y. So that's why this is called the del operator, because it's an action, it's a process, sort of more than it is like an object. But yeah, that's what del means. That's the del operator. And that's divergent curl. So let's make up a vector field, and then we'll see what happens when we take the divergence of it and take the curl of it and what those things look like. Okay, let's do f, x, y. This is the vector field version now. Let's go straight to 3 dimensions. We'll go big. I think you have to be in 3 dimensions to have a curl, because the curl is the cross product, and you can only do cross producty things if you have a 3-dimensional vector. So we have, I need to make this up. Let's do x squared y, y squared z, z squared x. Just smash a bunch of letters together there. Get ourselves a nice fancy vector field. So the divergence is what happens when we take the dot product of our del operator and f. This is the divergence of f. And to do this, we're going to do the partial derivative with respect to x of this piece, x squared y. And we're going to attach an I, that's not an I, we're going to attach an I to that. And then we're going to do, or no, we're not, no i's. Dot product, the result of a dot product is not a vector. Forgive me. We're just going to take the partial derivative with respect to this, or the partial derivative of this with respect to x, and we're going to do the partial derivative with respect to y of this, and we're going to do the partial derivative with respect to z of this, and then we're going to add them all together. That's what the dot product means, right? So these partial derivatives are the components of del, and these functions are the components of f. And so the dot product means you combine those things piece by piece and then add them all together. So this result would be 2xy plus 2yz plus 2zx. And then that's it. This is the divergence. One thing to note about the divergence is that this is a scalar. The output of this divergence is not a vector. It's just a number. And that number, I say number, it's a scalar valued function. It is a function whose output is a number. So if you pick a point x, y, and z in 3 space, and you calculate the divergence of it, you'll get some number. Based on the size of that number, that'll tell you whether that point you've chosen in 3 space is a source and it's pushing things out of it, or it's a sink and it's pulling things into it. That is what this tells you. So let's talk about the curl. The curl of f is the cross product of del and f. So for this one, we remember cross products. We're going to take our I and our j and our k, and then we're going to take the components of the first vector. So the partial derivative with respect to x, partial with respect to y, partial with respect to z, and then we're going to do the components of f. So x squared y, y squared z, z squared x. And we're going to take the determinant of this 3x3 matrix to get our cross product. The result of this will be a vector. So we're going to expand across the first row here. So that's going to be the derivative of this with respect to y. Which is 0 minus the derivative of this with respect to z, which is going to be y squared. That is our I component. And then we're going to get to the j component, which we sort of naturally just subtract. And it'll be the derivative of this with respect to x, so that'll be z squared, minus the derivative of this with respect to z, which is 0. That's my j component. And the k component is going to be derivative of this with respect to x, so 0. Derivative of this with respect to y, so x squared k. So we have, with a little bit of simplification, negative y squared I, negative z squared j, and negative x squared k. This is a vector field that can help us determine how and whether things are rotating at individual points across the xy plane. Sometimes you get the curl of a vector field is 0. That means that that vector field is irrotational. You can drop anything into that vector field and nothing will rotate. Things might move around, they might shift back and forth or get pushed out or pulled in, but they won't spin. So that's divergence, that's curl. Should I do another set of examples? I probably should. We're at 17 minutes though, so I'll make a separate video for that. Stay tuned.